Welcome to the deep dive. We take your chosen sources and, well, we dive deep to give you the core insights.
That's the idea.
Today, we're jumping into heights and distances. Now, I know what you might be thinking math flashbacks, but hold on.
Yeah, don't worry.
This isn't just abstract stuff. It's actually about how we use angles and a bit of trigonometry to figure out real-world sizes and distances.
Things you can't just walk up to with a tape measure.
Exactly. We've got some great source material here, examples, problems, diagrams, all focused on these ideas called the angle of elevation and the angle of depression.
Our mission really is to see how these simple-sounding angles let us measure, huge towers or find boats way out at sea.
Okay, so let's start with the basics from our sources. First up, line of sight.
Right. Pretty intuitive, really.
Yeah.
It's just, if you're looking at something, say, the top of a flagpole, it's that imaginary straight line from your eye right to that point.
Simple enough. Now imagine a perfectly flat horizontal line coming straight out from your eyes, like your horizon line. If you have to tilt your head up to see that flagpole top, the angle between that flat horizontal line and your upward line of sight, that's the angle of elevation.
Makes sense. Elevation looking up. Our page 1 diagram shows this as angle ACB.
And the opposite, if you're standing on, say, a cliff looking down at something.
That's the angle of depression. Same idea, you've got your horizontal line from your eyes, but now you tilt your gaze down. The angle between the horizontal and your downward line of sight is the angle of depression.
Like angle DEC in that other diagram on page 1 with the person on the tower.
Exactly. Eyes down.
Now here's a really neat part our sources highlight. The angle of elevation from point A up to point B
is exactly the same as the angle of depression from point B back down to point A.
Right. Page 1 mentions angle ACB equals angle DAC. It's like a perfect symmetry.
And that symmetry is super useful. It means we can often switch perspectives in a problem to make it easier to solve. We're basically talking about the same angle, just viewed from a different spot.
Okay, let's see it in action. Problem 1, page 1, we've got a vertical tower, and it casts a shadow.
And the key detail is the shadow's length is the square root of 3 times the tower's height.
So if the tower is x meters high, the shadow is root 3 times x meters long. The question is, what's the angle of elevation of the sun?
All right, picture it. Tower straight up, shadow flat on the ground that forms a right-angled triangle. The tower height x is the side opposite the sun's angle of elevation.
And the shadow, root 3x, is the side adjacent to that angle.
Exactly. So which trig function relates opposite and adjacent?
That'd be the tangent. Tan of the angle equals opposite over adjacent.
Right. So tan theta x divided by root 3x.
The x cancels out.
Yep. So tan theta equals 1 over root 3.
And the angle whose tangent is 1 over root 3, that's 30 degrees.
Bingo. So just knowing that ratio tells us the sun's angle.
It's pretty cool. You can imagine ancient people using shadows like this, maybe, to track time or seasons.
Absolutely. Simple geometry, powerful results.
All right.
Okay, let's try problem 2 on page 2. Different setup.
Here, we have someone standing 120 meters away from the base of a tower.
And they look up, measuring the angle of elevation to the top as 30 degrees.
And the goal is to find the tower's height.
Okay, same idea. Right angle triangle again. We know the angle, 30 degrees. We know the adjacent side, the distance, 120 meters.
And we want the opposite side, the height. So tangent again.
Looks like it. Tan 30 degrees equals height over 120.
And tan 30 is 1 over root 3. So height equals 120 times 1 over root 3.
Which calculates out, let's see, about 69.28 meters.
So again, just knowing a distance and an angle gives us the height. That's basically surveying, isn't it?
That's a core principle of it, definitely. Measuring things you can't easily reach.
All right, let's look at problem 3, page 2. Observation tower, 180 meters high. And there's a boat out there.
Part 1. From the top of the tower, the angle of depression down to the boat is 29 degrees. We need the distance from the boat to the foot of the tower.
Okay, angle of depression. But we know that equals the angle of elevation from the boat up to the tower top, right?
Exactly. Use that symmetry. So, from the boat's perspective, the angle is 29 degrees. The opposite side is the tower height, 180 meters, and the adjacent side is the distance we want.
So tan 29 degrees equals 180 over the distance.
Right. Rearrange that. Distance equals 180 divided by tan 29. Plug that in.
Gives about 325 meters.
Roughly, yeah.
Yeah.
So you can see how this is useful for navigation, maybe figuring out how far offshore something is.
Makes sense. Now, part 2 flips it. The boat moves. Now it's exactly 200 meters from the foot of the tower.
And we need the new angle of depression from the tower down to the boat.
Okay, so this time we know the opposite, tower height, 180 meters, and the adjacent distance, 200 meters. We need the angle.
Still tangent. Tan theta equals opposite over adjacent. So tan theta equals 180 over 200.
Which is 0.9.
Right, so theta is the angle whose tangent is 0.9. You'd use an arctan function on a calculator for that.
And the source says that comes out to about 41 degrees and 59 minutes.
Yeah. Notice the boat got closer from 325 meters to 200 meters, and the angle of depression got bigger from 29 degrees to nearly 42 degrees.
That feels right. The closer it is below you, the steeper you have to look down.
Exactly. Okay, so those handle single objects pretty well. Shall we move to scenarios with multiple points?
Yeah, let's add some complexity. Problem 4 on page 3. Two people, both on the same side of a 70-meter tower.
One measures the angle of elevation to the top as 25 degrees, the other measures 50 degrees.
And the question is, how far apart are the two people?
Okay, visualize two right-angled triangles here, both sharing the tower as their vertical side.
Height, ability meter.
Right. Let's call the person further away A and the closer one B. The tower base is Q.
For person A, the angle is 25 degrees. We can find their distance AQ using tan 25 equals 70 AQ.
And for person B, the angle is 50 degrees, so tan 50 equals 70 BQ.
So we calculate AQ and BQ separately. AQ comes out around 150 meters.
And BQ is about 58.7 meters.
Since they're on the same side, the distance between them, AB, is just the difference between those distances. AQ minus BQ.
150 minus 58.7 gives about 91.3 meters apart. Yeah. So different angles from different spots. Let us figure out the spacing between the observers. Notice the person with the bigger angle, 50 degrees, is closer.
That makes sense. Now, the source also mentions another exercise, exercise 22A, problem 4. Similar idea, but the people are on opposite sides of the tower.
Right. Towers, 50 meters angles are 30 and 38 degrees. In that case, you'd find each person's distance from the tower base.
And then add them together to get the total distance between the people.
Exactly. The geometry tells you whether to add or subtract. You just have to picture it carefully.
Okay, now for something dynamic. Problem 5, page 4. A tower's shadow gets longer.
Specifically, it increases by 10 meters when the sun's angle of elevation drops from 45 degrees down to 30 degrees.
And we need the tower's height. This sounds like it involves two different triangles again.
It does. Let h be the height. When the angle is 45 degrees, we know tan 45 equals 1. So tan 45 equals h, original shadow length. That means h equals the original shadow length. Let's call it x. So h is x.
Okay, that simplifies things. Now, when the angle drops to 30 degrees,
The shadow length is now x plus 10. And tan 30 equals h, x plus 10. We also know tan 30 is 1 over root 3.
and since h equals x, we can substitute h into that second equation. So 1 over root 3 equals h plus 10.
Perfect. Now it's just one equation with h. We need to solve that. Cross multiply.
H plus 10 equals h root 3.
Rearrange to get h.
You get h root 3, 1 equals 10. So h is 10 root 3, 1.
Which the source calculates is about 13.66 meters.
Yeah. So the change in the angle combined with the change in shadow length let us find the fixed height. Pretty clever.
Okay, problem 6, page 5. Back to a cliff 200 meters high. Observer sees two ships.
Part I. Ships are on the same side. Angles of depression are 45 degrees and 30 degrees. Find the distance between the ships.
All right, angle of depression 45 degrees means angled elevation from that ship is 45. Tan 45 is 1. So that ship's distance from the cliff base is equal to the height, 200 meters.
Good. For the other ship, angle of depression 30 degrees, so angle of elevation is 30. Tan 30 equals 200 distance. Distance equal tan 30, which is 200 root 3.
About 346.4 meters. Right, since they're on the same side, the distance between them is the difference. 346.4 minus 200.
Which is 146.4 meters.
Okay. Now, part 2. What if the ships were on opposite sides of the cliff?
Then we just add their individual distances from the cliff base.
Exactly. So it'd be 200 meters plus that 346.4 meters.
Giving 546.4 meters total distance between them?
See how crucial the setup same side versus opposite sides is?
Definitely changes the final step. Okay, problem 7 adds speed and time. A car approaching a tower.
From the tower top, the angle of depression changes from 30 degrees to 45 degrees over 12 minutes. Cars moving at a constant speed.
The question is, how much longer until the car reaches the tower?
This one's a bit more involved. Let h be the tower height. When the angle is 45 degrees, the car is distance h away, since tan 45 only is 1.
Okay.
When the angle was 30 degrees, the distance was h tan 30, which is h root 3.
So the distance covered in those 12 minutes is the difference. H root 3 minus h.
Right, but the car's speed be v, distance speed time, so h root 3 1 equals v 12.
We want the time it takes to cover the remaining distance h. So t equals hv.
From our first equation, we can find an expression for hv. It's 12 root 3 1.
So the remaining time t is 12 root 3 1.
Exactly. And if you calculate that value,
Comes out to about 16.39 minutes.
yeah, It's cool how we can bring time and speed into these trig problems.
Very neat. Okay, problem 8, page 6. This one sounds a bit different. Cloud, lake, reflection.
Yeah, a bit more abstract maybe. Observer is 25 meters above a lake.
Angle of elevation to a cloud is 30 degrees. Angle of depression to the cloud's reflection in the lake is 60 degrees. Find the cloud's height above the lake.
Key idea. The reflection appears as far below the lake surface as the cloud is above it. Let h be the cloud's height above the lake.
So the cloud is h 25 meters above the observer.
And its reflection is h plus 25 meters below the observer's level. Let it be the horizontal distance.
Okay, two triangles again. Tan 30 is 1 root 3 and tan 60 is root 3.
And tan 60 is h plus 25d.
We know tan 30 is 1 root 3 and tan 60 is root 3. We have two equations, two unknowns, h and d.
We can solve for d in both, or isolate d in one and substitute. Let's say from the first, dh 25 root 3.
Sub that into the second, root 3 h plus 25,
Okay.
h 25 root 3.
Multiply both sides by h 25 root 3. You get 3h 25, h plus 25.
3h 75 is plus 25. That gives 2h equals 100.
H is 50 meters. The cloud is 50 meters above the lake.
Wow, that worked out cleanly using the reflection was clever.
It's a classic setup for these kinds of problems.
Yeah.
Okay. Problem 9, page 7. Person walking towards a tower.
Initially, the tangent of the angle of elevation is given as 35.
Then they walk 50 meters closer, and the tangent becomes 45. Find the tower height.
Let height be h. Let initial distance be x. So first equation, h equals 35.
Second position, distances by 50. So h by 50 of 45.
Two equations, two unknowns again. From the first, maybe solve for x. X equals 5r3.
Good.
Yeah.
Substitute that into the second equation. H, 5 arch 3, 50 equals 45.
Now solve this for h. Bit of algebra. Multiply by the denominator. 5h is 4. 5r is 3, 50.
5 arch, 20 arch 3, 200. Multiply by 3, maybe 15 arch, 20 arch is 600.
That gives 5x 600. So h equals 120 meters.
There we go.
Yeah.
Another way changes in observation can reveal dimensions.
Okay, last one. Problem 10, page 7. A pole and a tower.
Pole is 20 meters tall. From the top of the pole, you look up at the tower top angle of elevation, 60 degrees.
And from the top of the pole, you look down at the tower foot angle of depression, 30 degrees. Find the tower's total height.
This combines both angles. Let's use the angle of depression first. From the pole top, 20 meters high, down to the tower base, 0 meter high, angle is 30 degrees.
That forms a right triangle where the opposite side is 20 meters, the pole height. The adjacent side is the horizontal distance between pole and tower.
Right, so tan 30 equals 20d. That means d equals 20 tan 30 equals 20 root 3 meters.
Okay, we have the horizontal distance. Now use the angle of elevation 60 degrees, looking up from the pole top to the tower top.
In that right triangle, the adjacent side is still negate 20 root 3. The opposite side is the part of the tower above the pole's height. Let's call it 8 diff.
So tan 60 is 8 diff d.
Tan 60 is root 3, so h diff d root 3 equals 20 root 3, root 3.
Root 3 times root 3 is 3. So h diff equals 23 equals 60 meters.
That's the height difference. But the tower's total height
It's that difference plus the height of the pole we were measuring from. So 60 plus 20.
equals 80 meters. Total tower height.
Nice. That one brought together both angle types quite well.
Yeah, it shows how you can break down more complex structures.
So wrapping this up, the big takeaway seems to be the power of these angles, elevation and depression, combined with just basic trig-like tangent mostly.
To let us measure things we can't physically get to. Heights, distances, separations.
It really is like a mathematical superpower for understanding the scale of the world around us.
Absolutely. And these aren't just textbook tricks. As we hinted, they are fundamental to surveying, navigation, astronomy. So many fields rely on these core ideas of indirect measurement using angles.
It really makes you think, though. How far can we push these basic principles? Imagine using them for mapping planets with satellites or guiding autonomous cars. What sort of new complexities pop up then?
Yeah, factors like curvature of the Earth, atmospheric distortion, processing speeds for moving objects. It definitely gets more complicated.
And just for you listening, next time you're out and about, look around. Notice when you're looking up at a building or down from a bridge. You're experiencing angles of elevation and depression constantly. What could you figure out if you just knew one distance or one angle? It's kind of amazing how much geometry is just hiding in plain sight.